I think it's 3 p.m., so I think we can get started. Yeah, hello everyone. I'm very happy to get here to talk about how we scale Postgres at OpenAI. And I'm Bohan, and a member of technical staff from OpenAI. And yeah, so this talk I will title the talk is about how we scale Postgres to the next level at OpenAI. And before this talk, I want to appreciate my team members, Sicheng, Chaoming, Chengdong, Dimitri, Kai, Qi, Ben, and Venkat, and many more at OpenAI infra team. And thanks for them to make Postgres super reliable and scalable. And also, we also thanks the other Postgres team, and thanks for their support. Okay, let's get started. So I will talk about the background, like how we use Postgres at OpenAI, and then I will talk about the optimizations we did, how it scaled to millions of QPS in the unsharded Postgres. And I will also discuss some case study about the past Postgres outages, and also some feature requests we had for the community, like where Postgres could do better. A little bit about myself. I'm a member of technical staff at OpenAI. I joined OpenAI last August, and I've been working at Open for like 9 months. And before that, I was a co-founder at Ottertune. Ottertune is a startup. It's a spin-off from Carnegie Mellon University. It's basically a startup to optimize your Postgres and MySQL using machine learning. It's based on many years of research from Samuel Davis Group. And before that, I was a researcher from Carnegie Mellon Davis Group, where I worked with Professor Andy Powell and Dr. Dana Vinkin on the Ottertune research project. Okay, background. Postgres is a backbone of our most critical system at OpenAI. So if Postgres goes down, many of our key features will become unavailable. So in the past, we actually have several related incidents about Postgres, which had a significant impact to the service like ChatGPT. However, scaling Postgres to meet OpenAI's demands is not an easy task. So we basically operate on a single primary instance in error without sharding for a very, very long time until we encountered write scalability limits. Because for the single primary instance, you cannot scale writes. You can add the read replica to scale reads, but for the single primary, you cannot scale writes. So in the current single primary multi-replica architecture, write scalability remains a bottleneck. So what we did is that we basically moved some write-heavy workloads that are shardable to other systems. So for the read-heavy workloads, it's not easy to shard. So it's still running on a single primary multi-replica Postgres. And we don't allow adding new tables and workloads. So if you want any new workloads or features, we that user to use the new sharded system instead of the current unsharded Postgres. And we also did lots of optimizations to ensure the current architecture has sufficient runway to support existing really heavy workloads and future growth. I will discuss what optimization we did in the next few slides. Overall, we think Postgres is not ideal for really heavy workloads. But for OpenAI's really heavy workloads, it can scale very well, even with the current unsharded architecture. So why Postgres is not ideal for heavy workloads? I think there are some known issues in the Postgres MVCC design. It's multi-version concurrency control. So Andy and I wrote a blog article about that in 2023. So basically, the current MVCC design can have some inefficiency. For example, it can reduce the loss of a table or index float, and also make the auto vacuum tuning very complex and hard to tune. And And there are also version churn from tuple copying. So basically, right now, if you update a single field in Postgres, a single field in a row is basically need to copy an entire row, so which can have lots of the right application. And it also has some increased index maintenance overhead. So if you want to learn more about that, feel free to check out our blog article. And it's also difficult to scale replicas if you are write-heavy workloads. This is basically because for the write-heavy workloads, it generate if it's write-heavy, it basically generate also write-heavy log to ship. It can increase the replica lag. So for the current like Postgres design, it has some write applications. Like I mentioned before, like when you update a single field in a row, it basically need to copy an entire row. So it basically need to ship more write-heavy log compared to other systems. And the problem worsens as the number of replica grows because the network bandwidth can become a bottleneck. Let's say you have like 20 or 30 replicas, and the primary needs to send the log to all replicas. You can see the network can be a bottleneck in this case. However, for read-heavy workloads, right now it's still served by the unsharded Postgres in error. The question is how can it be possible like on the like for the OpenAI scale, which is still running on one single primary unsharded Postgres. So there are things we did. So first of all, we want to reduce the load on the primary because we only have one primary, right? So we want to reduce the load for both writes and reads. So we mitigate the write spikes in primary by migrating some write-heavy workloads that were shardable from Postgres to other sharded systems. And we also reduce the number of writes at application level. This is because of the sometimes we find some unnecessary writes because of some bugs in the application. You just do some silly things in the application, so it has some unnecessary writes. So we just optimize the application to make sure it only writes when it's needed. And we also use some daisy writes where possible to smooth out the write spikes. Also, when you're backfilling a field, we basically set a rate limit for backfilling because if you don't set a limit, it can cause a problem. And right now we set a very hard limit. So sometimes you probably need a vehicle to migrate to backfill a field, but it is what it is in Postgres. That's for writes, and for reads, we off the read queries from primary to read replicas as much as possible. The idea is that for the primary, we don't want reads like consume lots of CPUs if they can move to read replicas because we only have one single writer. So we want to serve the writes instead of reads. But some reads still cannot be moved to read replicas. It still needs to stay in the primary because of the transactions. So sometimes we have a transaction, you have writes and reads in the transaction. So in this case, you cannot move these reads into to the read replicas. But we will make sure those queries, read queries are very efficient in my primary. So we make sure we don't have expensive read queries in this case. We also did some query optimizations. First of all, we want to avoid long-running idle queries by setting timeouts. So long-running queries can cause lots of issues. It can block auto vacuum and consume lots of resource. And we do find, in many cases, we do find some long-running queries. And we set the idle in transaction session timeout, which means that if the transaction or query is idle for I think right now we set it to 30 seconds. If it's idle for more than 30 seconds, the system will kill it automatically. We also set a statement timeout. This is because sometimes we find the query is actually idle it's actually idle in Postgres, but the status shows active. I'm not sure that's a bug in Postgres or not. I will discuss this later in my slides. But we find is that sometimes we find some idle queries, but the status is active in Postgres, so the idle in transaction setting timeout will not kill that. So we have to set the statement timeout as well. We also set the client-side timeouts. In the client-side, in the application side, we also have timeout. Another thing is that we want to avoid the OLTP query anti-patterns. So we see above the motivate joins in Postgres queries. I think the most expensive queries can join 12 tables. It's fine if the volume is low, but sometimes there is a spike in such queries, and it has a previous layer to selves because of that. So we basically want to avoid the expensive queries, expensive motivate joins, by handling joins at the application level instead of joining 12 tables in Postgres. And also with basically the user that will not write the raw queries on Postgres, and most of the cases they are using ORM. But the thing is that when using ORM, it can easily lead to inefficient queries because when you write the ORM code, you don't have an idea how to generate the underlying and SQL queries in Postgres. So it requires the user to use it very carefully and closely monitor the Postgres queries. Another big change is a single point of failure because we only have one primary. If the primary is down, it's basically a single point of failure. For read replicas, if one read replica is down, application can still route the queries to other read replicas. But for primary, we only have one, although we have standby, but we have one primary. If it's down, it will become a single point of failure. It's very it's very dangerous for the applications. So we try to do something to mitigate this. One thing we did is that we found that most of our critical requests are actually read-only, and it only need to get data from read replicas. So which means that if the primary is down, for most of the critical requests, you can still get resolved from read replicas. So if the primary is down, in this case, it will become a step 2 instead of the step 0, which brings down the whole service. It will become step 2, which means that most of queries can still work. It still can read from read replicas. That's how we mitigate the single point of failure from primary. We also have some categorize the low priority and high priority request. So we categorize the request based on its priority and importance. And high priority request means that it have a bigger impact on users when unavailable, so which can be a step 0, compared to low priority ones, which can just be a step 2. So we allocate the dedicated replicas for the high priority request to prevent them from being impacted by the low priority ones. So the idea that if for the low priority request, if there has some very expensive queries or spike of some queries in the low priority request, we don't want this request impact the critical service. So that's why we have a dedicated replicas for the high priority request. So we also set read limit on the multiple places, because previously a search from a single expensive query can bring down the entire instance and the entire service. So we have some expensive queries running on primary, like 12 with joins. The volume was typically low, so it's not an issue on most of the time. But sometimes there is sudden spike, either because of you deploy a new application or some requests, also requests on those queries. If there is a sudden spike in one of those queries, it can take down an entire instance. That's why we set a read limiter on the multiple places. We set a read limiter on the application level functions. to reduce the load during peak traffic. We also limit the creation of new connections to prevent connection pool exhaustion. Because sometimes we also see issues when the Postgres is running out of connections. That's why I also set limit on the connection as well. Another thing is that we allow user to set limit on specific query digest to control the impact of expensive queries. So for example, if we find a sudden spike for specific queries, we can just limit that query, so block the query completely, so that the query will not affect the bring down the entire instance. Connection pooling. So I think previously we had some issues now running out of connections. So that's why we have the PgBouncer as a proxy layer. So it acts as a connection pool and embodying the connection reuse. It can significantly reduce the connection latency. So we tested, we had some benchmark on that. So it basically, before using PgBouncer, it takes that 50 milliseconds to create a new connection. After a PgBouncer, it takes 5 milliseconds. It also reduces the number of connections because those connections can be reused by multiple applications. This is super important given the 5,000 connection limit on primary. So as discussed, we only have one primary. So I think Error has the hard limit, 1,000 connection limit on that primary. So yeah, so we need to use those connections really carefully to make sure the 5,000 connections is sufficient for us. So that's why the connection reuse and connection pooling is very important for us. And also, if the replica fails, the traffic will be automatically routed to other replicas. It is down in the proxy layer. So Proxy is responsible for that. Yeah, Schema is another very important thing for operating Postgres because we see some issues before because of Schema migration. So right now, only lightweight schema changes are permitted. So first of all, we don't allow creating new tables or introduce new workloads for the current unsharded Postgres. And we only allow adding and removing columns in tables. And it's a 5-second timeouts for the DDL operation. So really, it should finish within a second because it's just a metadata change. We want to avoid any rewrites for the entire table. So for example, when you add a column, if you set the default value to a dynamic value, that current timestamp, I think it will trigger the rewrite for the entire table. So we definitely want to avoid that. So yeah, so for the adding column, I think right now we require user to set it nullable when adding column. We also allow user to add indexes and job concurrently. And we find sometimes that a schema change can be blocked by some consistent queries. So if there are some non-running queries, I mean, we should take longer than 1 second. Is it consistently present on the target table? So the migration may get blocked and failed because of the timeout. So basically, we run this query, stack star from pgstack activity. We are query the target table name, and if it's running longer than 1 second, we run this query in Postgres. If we always find some queries present after present, and we basically think that those queries are blocking schema migrations. So if that happens, we want user to fix those queries in the applications, or at least move them to replicas so that it can unblock the schema change on primary. So with all those optimizations, so I think we are currently we are pretty happy about the Postgres. So we scaled our Postgres to the millions of QPS. It's powering OpenAI's critical service. And it also, we can also add dozens of replicas and with no increase in the replication lag. And we also, it can also achieve a low latency across the geo-distributed replicas because we need the replicas at different geo locations. For example, we have some replica on Australia and some replica on Asia to better serve the traffic there. So with this, I think we see the low latency across the geo-distributed replicas. And since I joined OpenAI, I think in the past 9 months, only one sub-zero related to Postgres. So especially because we have the unexpected huge write spikes in Postgres. And I think at that time, many systems also had issues because we don't expect the very huge write spikes there. Yeah, so besides that, we don't have any sub-zero since I joined OpenAI. And also gave us sufficient capacity headroom to sustain future growth. So the current architecture can still support us for a very long time based on our current traffic and growth. I want to thanks to the other Postgres team for their support on this journey. Yeah, so then I've discussed some like past the Postgres outage at OpenAI, and also the lessons we learned and how we address those challenges. The first common thing we saw at OpenAI is because of cache misses, because usually there's something wrong in the Redis there, and the Redis cache basically misses, and it increased the load in the Postgres because you need to get data from Postgres instead of cache there. And then the queries become slow, the app request becomes slow, and then timeout. And then in the application, if it's timeout, we request multiple times, and it generates more queries, more requests to Postgres. And basically, it's a very vicious cycle. Like, so you have more requests, you have more load in Postgres, and then query becomes slower, and then you have more timeouts, and then you have more requests because of retries, until the Postgres is not working anymore. So it's a very common pattern in OpenAI, and we did lots of things to address this challenge. First of all, we had the rate limit on Postgres and Postgres proxy. So basically, if you have more roles in Postgres, we had rate limit on proxy. Right? If there is too many requests, we just don't. We just reject those requests. So that's if there's a spike, we want to make sure it won't slow down the entire instance. We have rate limit on the Postgres and proxy because we want to break this virtuous cycle. We also rate limit on the app level, so which means like, okay, if the app request becomes slow and it's timeout. I think previously we tried timeout. We tried timeout a very small timeout. The biscuit will try very frequently, and I think we increased that time. We increased that a little bit, And also, more importantly, we have ready meet on the application. So if there are many requests in the application layer, we just job those requests when overloaded. So basically, we had to job the requests on the part 3 levels. First one is the Postgres and the Proxy layer level. If we set also requests, we job them. And we also job requests on application level. Is to break this vicious cycle. So another case is that sometimes we see some expensive queries in Postgres. So we find some expensive multiple join queries in the primary. And the worst case is join at 12 tables. In most cases, the volume is very low. So in most cases, it just works fine. But sometimes there is a sudden increase in the volume of one expensive queries or multiple expensive queries. For example, if you launch a new feature and it somehow call those queries, and also it also get worse due to the retries, right? Because those queries are very slow, and if the request timeout, they will just retries multiple times. So in the past, we see a sudden increase in the volume of those expensive queries, and it's makes the Postgres primary CPU really high. It's just jumped to 95%, more than 95%. And then the Postgres primary core becomes super slow because of the high CPU, and it impacts the critical service of OpenAI. So we did multiple things for this case. First of all, we want to definitely optimize those expensive queries, because if you want to do join a 12 table scatter, Postgres is not a right system for this use case. So mostly I think we optimize these queries on the application level to break down those joins and join them in the application instead of the Postgres. And also we add some features so that we can allow blocking or ready meeting specific queries. So it can help us to fix the issue quickly. If we find some huge volume of some queries, we can just block those specific queries to make sure it won't impact the entire system. Another thing is that we want to avoid using primary for read-only requests to prevent a single point of failure. This is because of that. So if the primary is slow, if the most critical request can still serve from replicas, so it won't be a step 0 for us. So as discussed before, we avoid such single point of failure in primary by moving the most critical to move the most critical request to replica, so that if the primary fail, it will not impact the critical service. So another issue we found is that there was a huge spikes in writes, because we know that will be an issue. If there is lots of writes, we know that current unsharded Postgres architecture will have some issues. But so in the past we have the sudden a huge spike in writes, which we don't expect. We didn't expect, and it's increased the CPU usage to more than 90 or 95%. And also the replicas, that also increased a lot. So usually rapid lag is within 1 second. But on that incident, it basically lag increased to like more than 10 minutes. So which means that query become very slow on the primary. And for the replica queries, it becomes still because you have the large replica lag. So the query on replica is reading the still data. And also the new writes are not accepted because the saturation of the primary. So it's impacting the ChatGPT service because of that. Yeah, I think that's basically the only step 0 we see in the past 9 months since I joined OpenAI. Because we don't expect the sudden spike for the writes. We didn't expect there is a very huge volume of writes traffic. So yeah, so we did several things to optimize this case. So first of all, we optimize applications to reduce writes. Yeah, so basically we optimize optimizations. We see there are some unnecessary writes in the application. Yeah, basically some inefficiency in the application level. So also for some writes, some writes and reads, I think you can move to some other systems. Yeah, so we basically want to make sure in the application we can reduce the writes as much as possible. And we also move the replicas, requeries out of primary if possible. So yeah, we basically move more like requeries to replicas because the CPU spec here is not only because of the writes, it's also because the primary still serve many requeries. So by moving the requeries as much as possible from primary, so even with the huge spike of writes, I think the CPU usage will still be good in a good status. We also found that there are some write amplification because we found that we basically send more write head log to replica than we expected. And so we found there are many unused indexes which can increase the volume of the write head log. So we basically remove unused indexes to reduce write amplification. In this case, the primary can send less log to the replica. It can help the replica lags. So after limiting the write queries, we basically I think move just stop most of the write queries, and the primary CPU usage returned to normal. It went back to less than 10%, but the replica lag continued to increase. So which means that the replica the changes on the primary is not applied to the replicas. So after investigation, we found there's several reasons for this. The first of all, we found the network bandwidth saturation in primary because there was also the write head log there. It's not applied to and shipped to the replica. So and the network bandwidth is a bottleneck in this case. And some replicas, we see the disk IOPS saturation because for those replicas, it also need to read the queries. If it's not hit the cache in Postgres, it still need to read the data from disk. And when you apply the write head log to the replicas, it also needs disk IOPS. So for some replicas, we see the IOPS saturation in this case. We also see the high CPU usage in the write head log as standard. It's really strange because we already stopped most of the RAG queries, but we see the CPU usage is super high. So it's basically caused by a bug. So when this knob, the async standbys waits for sync replication, it is enabled by default, which means that the the primary need to send the red log to the standby first and get acknowledgement from standby. And then after that, it can send those red log to replicas. But in this case, there's some weird bug that because it needs to wait for the standby acknowledgement from standby. So there are usually leads to excessive spinning instead of streaming wall to replica. So the CPU is used by the spinning and wait for the standby acknowledgement from standby. So that's why the CPU usage is super high, but the red log is not sent to replicas. So I think that's a bug in error, and yeah, so it's already fixed. So so we basically scale up the instance size and network also network because we see the saturation in the network bandwidth and also the disk ALPS. We also did some network settings tuning to allow us to send more data from in a network, and also error help us fix the bug in the wall sender. After this, after fixing the bug, I think CPU usage dropped from not 90% to less than 10%. Okay, so in the last section, I will discuss like where Postgres could do better. So some feature requests from community, yeah, so the first thing is the observability. Because we find like it's really hard to get the P95 or P99 latency from Postgres. Right? You do have some such stats for the API in the API level, but for the Postgres, we don't have. It's not easy to get those percentile core latency. So the PGStat statement only provides the average latency per query digest, but it don't have like a histogram or percentile latency for the query digest. I think we have some workaround to approximate the P95 and P99 given the current information we have, but it would be great if we have more information, like histogram or percentile latency in the PGStat statement, and we can get from there directly. Schema changes, yeah. So it also be great if the Postgres can store some schema change events, including the operations like adding or dropping columns or indexes or other DDL. So right now, I think we are using some monitoring tool for such purpose. But it would be great if the Postgres can store those information directly, so that we have more accurate we have better monitoring monitoring and tracking of schema change. Yes, it's very important for optimizing and monitoring our service, because sometimes the query can become slow just because of you add an index or remove index or add a column or something like that. So it would be great if we have such information instead of Postgres. Another thing we want is that we want some feature to disable index, because as I said, we try to drop some unused indexes because it increases maintenance cost and it also has more amplification. And we want to drop the unused indexes for better performance. However, to minimize the risk, we prefer to disable those indexes temporarily and monitor performance before actually dropping them permanently. So I think currently Postgres does not support disable indexes, which means that we need to, if we want to disable indexes, we have to drop the index. And if dropping index makes the application slow, and we have to recreate it manually as a fallback. But sometimes, like for the large indexes, it can take a long time to recreate the index. Yeah, I think there's some hacky way. I searched it on the Stack Overflow or ChatGPT. There's some hacky way to do that. Yeah, but it's good to have some official some command to do that. Also, it's also risky to because we don't want to do anything hacky on the production databases. Yeah, we want it to be well tested. Yeah, another thing is that I'm not sure that's a bug or not, because sometimes we usually found some active queries that have been waiting on the client for a very, very long time. So that's some stats from our monitoring tool. You can say for this query, it's running for more than 2 hours, so 2 hours, 23 minutes. It's active for more than 2 hours. And the wait event is client read. It's indicating that the query is waiting for a request from the client. And the wait event group is network, and the wait event type is client. And state is, you can say state is active, which means it will not be killed by the if you set the idle in transaction session timeout, it will not be killed because state is active. It's not idle. And if you compare the query start and state change, you can see that basically the query start, the timestamp is same as query change, state change, which means it's changed to this wait event state that client read this state and wait for 2 hours and 23 minutes. And it's not killed by the idle session timeout. I'm not sure it can be killed by statement timeout, but yeah, I'm not sure it's a bug or not in Postgres. And I think it should be, in this case, I think the state should be idle in transaction instead of active. But in reality, you find many queries, the state is active. Yeah, if it's not a bug in Postgres, I'm curious how to kill it automatically in Postgres. Yeah, that's the one issue we found. But it's not impact the performance at all. So we find some queries that have non-running queries and running for 2 hours, but it really is not the root cause of our the issues in Postgres. So it's not causing any issues right now, but it's just weird. It's just yeah, it's because usually when we find the non-running queries to investigate our Postgres, in most cases we find this case. It's active and it's waiting for kind. Yeah, and it's not killed. It's running for more than 2 hours. Another thing is automatic knob tuning. Yeah, this is related to my work at AutoTune because we found that Postgres default knobs are notoriously bad. So yeah, so I think we want better default knob values. It can be either very heuristic based or others. Yeah, even rule based is fine, but I think it should be easy to it's not hard to get better default values, knob values. And the more advanced thing is that if we can have some adaptive knob tuning based on workloads, like auto vacuum, because it's really hard to tune auto vacuum, and there are many knobs related to auto vacuum. And auto vacuum is already important for the rate heavy workloads if you have lots of rates. So I think there are also there are some examples in the industry. So yeah, we found that on the managed cloud providers like AWS or Azure, actually the default values are much better than open source Postgres. And I think AutoIDB also have some feature like adaptive auto vacuum tuning. So it would be great if we can have such feature in the open source the Postgres. Okay, we have 5 minutes. So here is what we find at OpenAI. So at OpenAI, we're proving that the Postgres can scale very well for read-heavy workload. It can scale to support massive read-heavy workloads, even without sharding. Yes, without sharding, using a single primary writer. It's a read-heavy workload, right? So for the write-heavy, I think there are also issues there. But for the read-heavy, the Postgres can scale very well. So if you are a developer or building startup, just start with Postgres for read-heavy workloads. I think Postgres right now is probably the default choice for developer. You can use Postgres for a very long time. If you build a startup for really heavy workloads, just start with Postgres. You can use it a very long time, right? If you see a scalability issue, just scale up the instance size. You can scale it to support it to a very large scale. If sometimes the Postgres become bottleneck, congratulations. It basically means that you are building a successful startup and your workload that is really high. So it's a good problem at that time. Right? I mean the Postgres issue, the relativity is also a great problem. If you have scalability issue, right? It's really because many users are using your product. Because previously I built a startup at Autotune, I know the database issue is really good. It's a good problem to have. Thank you. So we have about 3 minutes left. Any
We have
questions?
3 minutes for questions.
Yeah.
Thank you. Regarding this stale query that is still active, could this have something to do with TCP keeper lives that are not working on your end?
So you mean it's still queries?
The active query that is
active query.
Yeah.
Yeah.
So it's waiting on client reads.
It's waiting for client read. Yeah.
So for 2 hours, but isn't doing anything, right? This is what you said.
Yes.
So I'm wondering if the TCP connection is broken for whatever reason, and TCP keeper lives are not turned on your server backend.
Sorry, can you repeat your question?
The TCP keeper lives.
TCP keeper lives. I think it's set by default.
Because the defaults are insanely high, so.
I think it's set by default. I think we just use the default error Postgres settings for that.
Yeah, which is literally hours. So this may be.
Because I also find some similar issue on the GitHub, and someone post some similar issues, but I don't find a good answer there. Thanks for your information.
Any more questions?
Could you go back to the slide with the right? Sorry, the slide with the right amplification. Well, you mentioned that one. Optimize applications to. Next one, maybe.
This one?
Yeah.
Okay.
Optimize applications to reduce writes.
Yes.
Do you have a couple concrete examples for us, like something that you personally? What kind of example can you give us that really gave you?
It's just some application. There's some. For example, it's just actually insert twice or update twice for the row. And also that's one example because we find some bugs in the application. It just updates twice or 3 times. It's just unnecessary writes in the application level. Another thing is that what we did is that we have some daisy writes. For example, when you at ChatGPT, when you like start some features, you update something, right? You don't so it will only write the update the database when you use that feature. Sometimes daily writes to smooth out the writes in the database, if that makes sense.
Sorry, we are above time. You can catch Bohan in the lobby for further questions.
Thank you.
Thank
Appreciate it.
you.
Thank you. Yeah,
This is your speaker swags.
Oh, thank you. Thank you. Yeah, I'm here like all day, so feel free to chat if you have any more questions.